like to introduce Joe Stringer, who will be presenting the eBPF Systems Revolution. Joe is principal software engineer at Isovalent and traveled from California to join us today. This will be his first time presenting at NANOG. Welcome to stage, Jay.
Hi everyone, thanks for sticking around for the last session of the day. My name's Joe Stringer. I've been working on software-defined networks for pretty much my entire career. I've worked on Open vSwitch, the Linux kernel, and I now co-maintain the Cilium project. And so for the better part of the last decade, I've been working on BPF. So that's what I want to talk to you today about. I want to give you an overview of what eBPF is and why I think it's providing a lot of value in systems innovation and in building new host logic, including in the network. And I want to do a quick dive into a couple of specific open source projects that are using eBPF to be able to provide networking functionality. And then we'll have a little bit of a look at future-looking areas of active development in the eBPF community. So what is eBPF? eBPF makes the OS, the operating system kernel, programmable in a secure and efficient way. And so software engineers can build a program which you then push into something like the Linux kernel and attach to specific events that are occurring in that kernel. So example on the screen is monitoring all of the times that a process executes on the system, and then just adding that to some sort of a metric to be able to understand when those processes are being executed. But it supports a wide range of different events, including, notably for this audience, different network hooks. So why is eBPF important, and what makes it different from previous approaches? So previously, if you had some interesting idea about how you might want to extend the kernel and maybe do something interesting in the network on the host, you would go and have a chat with your local friendly Linux developer. You would explain the idea to them, and maybe they'd go away and hack and build that implementation. But then for that feature to then be included into the Linux kernel, they need to get the community on board with that same idea. Now, this is well and good if you can come up with generic building blocks that are supported by a wide range of different people trying to all solve similar problems. But it can be a lot more tricky if you have more niche use cases or things that are specific to what you want to do with the kernel. But let's say you overcome those hurdles, you get the logic into the kernel. It can still be a number of years before operating system vendors actually distribute a new kernel version that has that feature. And so maybe by that time you've moved on. So the difference with a eBPF style approach is that you can now go and have a chat with your eBPF programmer, has many of the same skills as your Linux developer, but using this programmable layer in the OS kernel, you can then load that functionality into the kernel without even rebooting the system. So this innovation cycle is then much, much quicker. You're talking about days or weeks rather than kind of months or years. So rather than having an innovation cycle that is tied more at the scale of kind of hardware and operating system kernels, you're moving more into kind of a software life cycle. So how does eBPF work under the hood? There's two primary components of eBPF. One part is a language that allows you to build that functionality you want to load into the kernel. And then the second part is that runtime that actually executes that logic in the kernel. So let's briefly look at the eBPF language. So typically you would write an eBPF program in much the same way that you would write kernel code. C is a popular language of choice. You would pass this through a popular open source compiler like GCC or CLAN. And then this emits a bytecode, a BPF bytecode representation of that functionality. Additionally, there are a range of SDKs for popular languages that allow you to interact with that BPF program when it is running. So you can share data between the module that's running in the kernel, the eBPF program, and user space components that then measure metrics, pass them on to other systems, or even define the control of how that eBPF program should behave at runtime. So eBPF is a RFC now, and yeah, there's various different SDKs you can use for popular languages. So once you've generated this bytecode under the hood, you attach that bytecode, that feature into the operating system kernel. And there's three primary steps that the eBPF programs go through at this point. First, the kernel actually verifies the safety of that eBPF program. So the eBPF program is not going to crash the kernel, access memory out of bounds, deadlock the system. Once the kernel has approved that eBPF program, it then transpiles that eBPF code to the native instruction set of the host itself. And there's a range of different JIT compilers for different popular architectures. At that point, that efficient code can then be attached to a specific event in the system, like whenever you receive a network packet on the NIC, or whenever an application makes a connect call or starts generating a packet. So taken together, you get safety and security from the runtime verification. There's exploration in program signing as well. The JIT compilation makes the execution of this functionality very efficient on the host operating system. And there's a range of different data structures that are also available to eBPF programs that can be shared with user space components in order to solve problems in an efficient way. And finally, it's a portable generic bytecode that can run on a variety of different architectures. So eBPF is used today in a wide range of industries, from online retail, financial services, clouds, a whole bunch of different things. And we've been building a community of over 25,000 different people who are either building eBPF programs or using eBPF-based software. And I'll tell you more about the Slack later on in the talk. Well, let's take a look at a couple of real-world examples of using eBPF to solve problems in the network. So Katran is a project that was launched by Facebook, now Meta. And the goal here is to build a layer 4 load balancer. And so when you take the traffic into from your edge, you spray that across a set of layer 4 load balancers, and those then subsequently translate virtual IPs into the real IPs of different layer 7 load balancers in your system, which can then perform further operations and ultimately deliver that traffic to the applications that need to serve the requests that are coming in from the user. So at the time that they were looking at building this, they were using IPVS in the Linux kernel, and they found that there was quite considerable CPU usage on the nodes that were running this layer 4 load balancer. And so along with that came some deployment sort of struggles. They found that they had to dedicate certain instances, certain nodes within the cluster towards specifically the layer 4 load balancing functionality, and then separately deploy the layer 7 load balancers. And managing this ratio of servers created a number of challenges. There's various different things around availability as traffic patterns change, and as you manage your planned outages and so on. And finally, if you wanted to optimize this implementation, it would require kernel reboots. So using eBPF, they rebuilt this layer 4 load balancer, and that's the project Katran. And this allowed them to significantly increase the performance. And part of the way that they did this is using a technology called XDP, which is Express Data Plane. And I'll talk about that briefly in a moment. And so by reducing that cost of the layer 4 load balancing on this commodity server, they were then able to also co-locate the layer 7 layer 4 load balancers on the same systems, thereby easing some of the operational aspects of this problem space. At the same time, this was around when consistent hashing was becoming quite popular, and so they integrated some of the newer, at the time, algorithms for handling the spread of traffic at layer 4. And of course, the management aspects became easier when they could simply swap new versions of this data plane into the operating system kernel without rebooting. And if it turns out that one build is bad, you can also roll back just as easily. So I mentioned XDP. XDP, what is it? So this is a programmable layer close to the NIC inside the host. And it's inspired by DBDK to try to minimize the number of instructions that a CPU has to actually execute in order to handle forwarding and routing and so on the host. It also aims to avoid unnecessary memory allocations. One of the differences between DBDK and XDP is that XDP assumes by default that packets are coming into the host and they will be delivered towards an application, And so if you just pass traffic through XDP, that's the default path. So that means native applications will continue to work. But at the same time, it has alternative return codes for these programs that allow you to either drop packets directly there close to the NIC, or even reflect them back out a NIC on the host system. And so in a case like Katran, where they're doing a one-armed router, take packets in, perform a layer 4 load balancing decision, and then send the packets back out onto the fabric, this was really well suited. And overall, the behavior here is defined by eBPF programs, ultimately. So here's a couple of graphs that they'd presented at Scale conference a few years ago. And what they found when they switched from the previous solution to Katran was that they reduced the number of CPU cycles dedicated to the layer 4 load balancer on these systems by 7 times. And at the same time, they tripled the packet rate. So on the graph, you can see the thick lines are a number of servers running the old solution, and then the thin lines are the new solution. The top is higher is better. That's CPU dedicated to the idle process, which is effectively CPU that's then available to be handed to another workload on the system. So one of the interesting kind of points to this is that traditionally you might think that the flexibility of being able to build custom logic in your network might be a trade-off against performance, but here we see that we're actually able to gain a bunch of flexibility and also gain performance at the same time. Now I want to switch gears a little bit here and talk about Cilium. So Cilium is a network plugin primarily for Kubernetes environments, but generally in the data center. And it's used by all the major clouds in their Kubernetes offerings. So Cilium provides networking, security, and observability functionality. So this includes connecting workloads with one another within the cluster and across different clusters, connecting to virtual machines, and enforcing firewalling for those machines, transparently encrypting traffic between nodes in the environments, and finally, observing what's going on in the network. So it can generate data that you can then render a service graph that shows this application was communicating with this other application, and here's the latency, and here's the throughput, and so on between those applications. So broadly, Cilium works through a declarative intent model, like much of Kubernetes, and so there's various different constructs within the network and the environment that are declared in Kubernetes objects. And Cilium has some custom objects that it uses to manage its own configuration, including network policy. And then what you do is you run the Cilium agent on each worker node within that environment. And then those Cilium agents pull the high-level declarative intent from Kubernetes and then translate that into eBPF instructions that can then execute that functionality in the kernel. They also facilitate communication of information east-west between the different nodes about which application is where and so on. So ultimately, this allows us to synchronize that intent of how you think the network should work down into each individual node to implement the networking security and observability functionality that you're looking to use. So I want to talk briefly about the sort of numbers we're talking about here, just to give a sense of the churn and scale. So we're talking about potentially churning multiple, like perhaps tens of deployments on a node per minute. There may be 100 or more workloads on each of those nodes. There may be thousands of nodes in the cluster, which are connected through virtual IP services in the numbers of 10,000s. And you may be talking about 100,000 containers or more. And then rinse and repeat if you have additional clusters. And so in order to try to deal with some of those performance constraints, we've been doing a bunch of work on trying to optimize different aspects of the networking within the host. So one of the areas that we're focused on is in the load balancer. And so traditionally, before Cilium, it was very common to encode a large number of front-end and back-end services into IP tables rules in the host kernel. And as you start to get these into the numbers of thousands, the iteration of that linear list to try and determine how you should forward packets starts to create a performance cost between all of your applications in your environment. And so by avoiding linear iteration and switching to a hash-based model, we were able to drastically increase the performance. Another thing that we looked into, and we have implemented this in Cilium, is to apply the load balancing decisions at the socket layer. So it's when an application makes a connect call, rather than at the packet layer and implementing the logic there. And so this way you can significantly reduce the number of operations, the number of CPU cycles we spend per connection on that load balancing decision. We've been doing a bunch of work on the routing stack as well. So one of the things we find is that with the Linux kernel, it's built to be very kind of generic, and there's a lot of building blocks that you can customize to do what you would like to do within that environment. But that kind of generic building block kind of style of building the upper networking stack can incur a performance cost. And so a lot of that performance cost we are able to optimize away by just effectively building our own version of that functionality that only does the minimum necessary number of instructions to achieve the functionality we're looking for. And we do have a much more specialized use case when we're talking about a cloud-native environment. But one of the things we find is that people are very interested in being able to use existing routing daemons within the environment with this eBPF-based data plane. And so we built a hook that allows you to, from an eBPF program, introspect what the Linux kernel routing tables are going to do, and then we can perform the exact same routing decisions of what you've already configured. So you can take your existing FRR or other BGP routing daemons and so on that configure the Linux kernel and put them in place for your control plane, and then Cilium will just quietly accelerate the path underneath that. Finally, I want to talk briefly about scheduling. So in terms of how we're taking packets from a container or a VM and then handing those towards the network and optimizing that path. So I'll explore that in a little bit more detail. If I get the right direction, here we go. Okay, so one of the recent goals that we've had is to push to 100 gig line rate for a single TCP stream within the host. And so you've been able to do this for a number of years now with directly on the Linux host itself, if you just have the application running right there. There's a bunch of configuration. I'm certainly glossing over a lot of details here. But we found that when you introduced containers, the performance drops to around about 60 gig. So there's a performance cost there, and you might think that's natural. You're putting containers there, and that can obviously incur some kind of a cost. And so the challenge for us was, can we rethink this problem and eliminate that cost, ideally, or at least reduce it? So what we did was we gathered data around how the CPU is spending its time when it's handling packets within the host. And we generated this flame graph. So broadly speaking, left to right is the amount of time that is spent on a particular process within a particular function, I should say, within the Linux stack as it handles the packets. And then the height is the number of functions that it's executing. So each line represents another different function. And broadly, you can see two peaks here. The center and left are all part of the Ksoft IRQD. And so what actually happens, to explain this graph in different terms, is the application starts transmitting data towards the network. The Linux kernel forms a packet, a skbuf, that it's going to use to transport that data towards the network. And then it transmits that over a virtual Ethernet device. And so that goes from the container environment over to the host itself. Now, once it reaches the host side, it enqueues that packet onto this virtual Ethernet device. And at that point, the CPU that's actually handling that gives up and says, okay, my job is done here. And then later on, there's a different thread that comes along to complete the rest of the execution on the host side. So one of the things we said was, what if we do a run to completion model here instead? So we have the same CPU actually taking the packet all the way from the application down to the NIC. So long story short, this is what my colleague Daniel Borkman worked on. And at the same time, we did build a bunch of other optimizations around early departure time scheduling and different other optimizations. I won't go into those details. But the long story short is that we were able to actually reach that 100 gig single stream performance rate from a container over to the network. And so we put this into recent Linux kernel versions, and actually Meta in FOSDEM in February this year talked about a situation where they had an application that would take around 12 seconds, would have about 12-second latency for a particular operation at the 99th percentile. And when they switched from virtual Ethernet pairs to this new Netkit-based driver, that dropped down to just 0.1 seconds. So that's a pretty drastic improvement in the latency. And actually, ByteDance rolled this out as well. And what they found was that they were able to increase their overall throughput across their environment by 10%, which is pretty impressive numbers. So the next steps on this is to work on how to apply this similar techniques, but into the virtual machine. So if you have more isolated workloads. But yeah, I'm glossing over a lot of detail here. I'd encourage you to check out the talk linked on the slides there from KubeCon 2023, which has a whole bunch more detail about this and more. But as we wrap up, I kind of want to take a step back and give you a bigger picture about what eBPF is about and some of the active work going on in the community. So here's just a sample of some of the use cases we're seeing in eBPF. So eBPF is being used for Linux security modules for enforcing in secure cloud environments. It's being used for runtime security, both monitoring and enforcement, to mitigate various different CVEs, but from the host itself. It's being used in gaming devices to optimize frame rates to make the performance of video games much quicker. And finally, there's a range of different tools available in the BPF Trace project that allow you to introspect specific operations that are happening within the operating system kernel. Now, I've focused a lot in this talk about Linux, because that's the place that I kind of know best, but Microsoft has been working on eBPF for Windows for a number of years now. And they're big proponents also of the IETF effort to provide cross-platform, cross-operating system standardization of the BPF ecosystem. And so if you're interested in participating in that working group in the IETF, I'd encourage you to check out the link here and join the mailing list and join the sessions at IETF. Another organization that's doing a lot of good work in the eBPF ecosystem is the eBPF Foundation. So there's a range of sponsors here that are really want to see the this innovation that occurs with eBPF to continue and want to encourage that innovation in a vendor-independent way kind of going forward. And so there's various different initiatives that the eBPF Foundation funds, both in terms of directed development. They've published a documentary. If you go to ebpfdocumentary.com, that gives a great overview of what is eBPF and how is it changing the industry. And we also recently put out 5 different grants to research institutions around the world to improve BPF, both in scalability, static analysis, improving the safety of the verifier, and more. But to wrap up, so if I leave you with one thing, it's that eBPF is unlocking systems innovation. What you see on the screen is a range of different projects that are involved in the eBPF ecosystem. And if you go to ebpf.io, you can find a bunch of these projects. And maybe you're interested in participating in one of these projects. Maybe there's something there that you will find interesting to use as a user of eBPF, or maybe you want to contribute back. So it's been about 10 years of eBPF at this point. And it's been really exciting to see how the community has grown, how we've built a lot of really interesting system software across networking and beyond. And I'm really looking forward to the next 10 years of eBPF development. So with that, thank you all for your attention.
All right, thank you, Joe. It looks like we have a question over there. If you have questions, please use the 2 mics. Remember to state your name and the company, and then ask the questions.
Logan Blythe at Hedgehog. When you had the Netkit driver performance results and you had 100 gigabits per second, do you have a packet per second figure on that, or is it just?
I'm sure there are. I think if you look at the KubeCon talk, it might have that. There was another graph. I think that was probably also in gigabit. I mean, we can do the math. This is with like 8K frames and so on. So
we
yeah, but it was also single TCP stream, which I think was our focus. Because
Yeah.
you can always like spray across different cores and reach higher performance, right? But,
Yeah. And then are you aware of any comparisons between DPDK and eBPF?
yeah, I mean, I think they're quite different tools, I would say.
Yeah.
I wouldn't necessarily put them quite in the same category. You know, I think when you're building DPDK applications, you need to build a huge amount of like TCP stack and so on to be able to handle end-to-end packets.
Yeah. It's all
from that NIC, right? Whereas with the eBPF-based approach, the idea is it integrates a bit better with existing applications. So if you have other control or monitoring or whatever other systems that are running on the same host and potentially using the same NIC, you don't have to dedicate that NIC towards just eBPF. Like it's part of the system. It just operates as if eBPF is not there. If you write your program to allow that kind of interaction.
Thank you.
Thank you.
Wim Hendricks, sorry, Nokia. When you attach an eBPF program to the kernel, right? So you attach it to a hook.
Mm-hmm.
At some point, there was a challenge if you have multiple implementation or multiple, let's say, systems.
Mm-hmm.
Is that resolved in the meantime, that you can actually attach from different programs to the same hook, and that you can have, because otherwise you can have some of these conflicting systems, like if you do security or you have two different vendors that you want to hook onto it. Is that resolved in the meantime?
There are solutions.
Okay.
It is quite a tough problem to try to solve completely generically. Because ultimately, when you attach a program, and let's say it's handling packets on the network, right? If the first program goes and changes the packet content, it changes the IP address or the MAC address or something, that can have an impact on the second program. And so as a generic problem, it's a little bit hard. Like you do need to somehow figure out which pieces of logic make sense to include in each chained program, if you will. But the short answer, I think, to your question is that some of the newer kernel APIs for eBPF allow what they call improg, like multi-prog attachments. And with that API, you can define the ordering when you load. So you kind of say, oh, I know I need to load after a program that looks like this, and then you can manage that dependency there. And additionally, there are user space tools that allow you to determine ordering and manage all of that on top of those kernel APIs.
Okay, but I was interested in the multi-program attachment. In the meantime, that's available, it seems. Yeah. Okay. Thanks.
But yeah, it will depend on exactly which hook
you're
talking about. This,
what you want to do.
Cool.
Okay. All right. Thanks so much. That was fantastic. Thank you very much. Thanks, Joe.